Hi, I am Runyu from the Visa Lab of Arizona State University. This is the presentation for SmartDedup, optimizing deduplication for resource-constrained devices. This work is collaborated with my colleague Qirui and my professor, Dr. Ming Zhao. SmartDedup focuses on resource management on resource-constrained devices. Edge and IoT devices have two concerning characteristics: the data-intensive workloads and the limited on-device storage. The large data presented by the on-device sensors and applications has presented serious challenges to the limited on-device storage, which has limited I/O performance, capacity, and endurance. Deduplication might be the rescue to the above problems. So what can deduplication do? Deduplication can eliminate redundant I/Os and improve I/O performance. It can reduce flash writes and improve flash endurance. It can also remove redundant data and improve resource utilization. Deduplication has been widely used in the cloud. However, to adapt deduplication in resource-constrained devices, we must answer two questions. First, is there enough data duplication in the device workloads? And second, how do we exploit the data duplicates using only the limited resources that the device has? Gladly, SmartDedup has answered both questions, and let's look at them one by one. For the first question, to verify that there is enough data duplicates on the device workloads, we collected and analyzed long-term I/O traces up to 6 months from smartphones used by different users. This table shows some general information about the traces. From the table, we can see that first, real-world device workload is indeed quite intensive, with everyday I/O volume up to 16 gigabytes and everyday write volume up to 2.8 gigabytes. And they do have an impact on the storage performance and endurance. Second, we also find that all workloads have a good level of duplicates. You can see the duplication ratio is up to 47% for the entire trace. To understand the sources of the duplicates, we conducted a more in-depth analysis. We categorized files into 5 categories and analyzed which category contributes the most amount of duplicates. These two graphs here show the top 3 duplicate contributors for each trace. The top graph uses the percentage of writes to each category as the y-axis and the category name as the x-axis. The bottom graph uses the deduplication ratio for each category as the y-axis. In this graph, for example, for trace 1 in the yellow color, resource file contributes the most amount of duplicates. However, for trace 2 in the blue color, temporary file is the top duplicate contributor. So you see, duplicate sources differ by devices. We also conducted file-level deduplication and found that more than 80% of duplicates are from files that are not entirely duplicate. So we conclude a system-level deduplication across files and applications is necessary to remove all the duplicates. However, there are still challenges. First, the device has limited memory, and we may not have enough memory to store fingerprints to quickly detect duplicates. And second, the storage has limited performance and endurance, while deduplication incurs additional metadata operations. And third, many smart devices nowadays have limited power and energy capacity, while fingerprinting of deduplication consumes quite a bit of power. Our design, SmartDedup, a smart deduplication solution for smart devices, has addressed the above challenges. First, to achieve a good level of deduplication ratio without using too much memory, we designed a small in-memory fingerprint store and uses a large on-disk fingerprint store to complement it. And second, to improve storage performance and endurance, deduplication should be applied as much as possible, and we combine inline and out-of-line deduplication together for thorough deduplication. And third, to further save resources, we designed adaptive deduplication, which can adaptively tune the processing rate of deduplication based on resource availability and the workload characteristics. The bottom graph shows the overall architecture of our design. Next, I will give some details about SmartDedup. First, let's look at two-level fingerprint stores. In-memory fingerprint store maintains only important fingerprints, and fingerprints are indexed using a prefix tree. Prefix tree can index a group of fingerprints that share the same prefix. Indexing individual fingerprints takes too much space, while indexing a group of fingerprints can save a lot of memory. Also, the prefix tree can help support the two-level fingerprint stores. This graph shows our in-memory fingerprint store design. You can see the first 12 bits of the fingerprint are used as the index, and all the fingerprints that share the same prefix are grouped together under the same leaf node in the in-memory fingerprint group. Then let's look at the on-disk fingerprint store. On-disk fingerprint store maintains fingerprints that are not in memory, and it shares the same index with the in-memory fingerprint store. This can help save memory and facilitates the fingerprint migration, which will be introduced later. And the starting PBN that stores the group of on-disk fingerprints is added to the leaf node to represent the on-disk fingerprint group. So in this way, the leaf node points to both an in-memory and an on-disk fingerprint group. Fingerprints migrate between memory and disk on demand. An in-memory fingerprint store keeps the most recently used fingerprints. The traditional way of evicting one fingerprint from memory to disk happens frequently whenever a fingerprint is not found in memory and takes too much I/O overhead. To save this overhead, we choose to evict fingerprint in groups. Let's see an example here. Suppose now the in-memory fingerprint store is full, and we evict a group of fingerprints to disk. So in this way, a number of slots have been freed and can be used to store many fingerprints from the future requests before the next eviction happens. In this way, the eviction frequency has been reduced, and the I/O overhead has been saved. Then let's look at the hybrid deduplication. Inline deduplication works in the I/O path, and it can eliminate duplicate writes immediately. However, due to the limited resources on device, we may not run inline deduplication at full speed. Out-of-line deduplication, however, works in the background, and it can slowly but thoroughly eliminate all the duplicate data. However, it has limited improvement on performance and endurance compared to inline deduplication. So we choose to combine these two to make them work cooperatively together. Let's see how a write is handled here. When a write first comes in, we will first fingerprint the request and then searches the in-memory fingerprint store. If it is a miss, we will further pass the fingerprint or the request to out-of-line. Out-of-line deduplication then searches the on-disk fingerprint store for the fingerprint. If it is found in the on-disk fingerprint store, it is then promoted to memory. In case in-memory fingerprint store gets full, we will evict a group of fingerprints to disk. Then let's see how a read is handled. The native read path of deduplication system cannot utilize the duplicate data in the page cache, since page cache is indexed using LBNs, and it does not know that different LBNs may contain the same data. So it cannot avoid extra reads, even if the same data is already in the page cache. Let's see an example here. We have LBNX and LBNY. Both are deduplicated to PBNX and contain data DataX. So we first read LBNX. It will fetch the data from disk and read it into the page cache and then return the data. Then later on, we want to read LBNY. LBNY also wants to read DataX. However, although DataX is already in the page cache, it has to read from disk again. And thus, we have a duplicate read here. So how SmartDedup solve this problem? We optimize the read path to utilize the duplicate data in the page cache. We added a page cache index in the page cache to map from PBNs to the corresponding pages. So if a request looks for the data in the page cache and it is a miss, it will further search the page cache index. Let's reuse our previous example. So first we will read LBNX, and everything remains the same, unless this time we add the PBNX to DataX mapping in our PBN-based index. So later on, when we read LBNY, we first search page cache, and it is a miss. Then we will further search the page cache index using the PBNX. So this time, it can directly read the data from page cache, and we can save a read here. To further save resources, we designed adaptive deduplication. Based on the resource availability, SmartDedup can decrease the processing rate of deduplication to keep CPU and disk utilization under 100%. Also, it can decrease the processing rate of deduplication proportionally to the available battery life and completely disables deduplication in low battery state. Based on the current duplication level of the workloads, if the duplication level is decreasing, SmartDedup will work less aggressively and gradually decreases the processing rate. On the other hand, if the duplication level is growing, SmartDedup will work more aggressively and quickly restores the processing rate. So far, we have answered the second question on how to exploit data duplicates using only limited resources. And to evaluate the effectiveness of our design, we prototyped SmartDedup on commonly used file system of smart devices, EXT4 and F2FS, and we tested it on smartphones Nexus 5X and IoT platform Raspberry Pi 3. We used both benchmarks and real-world workloads and compared our work with state-of-the-art deduplication solutions, DMDedup and SayFTL. DMDedup is a block-level deduplication solution which supports flexible metadata backends, while SayFTL is a deduplication solution for resource-constrained FTL layer. Let's first look at the FIO experiment on Nexus using EXT4. This graph shows the write performance. The y-axis is the throughput, and the x-axis is the variation of percentage of duplicates from 0% to 100%. In this graph, SmartDedup is shown in the purple bar, and the higher the better. You can see SmartDedup always performs the best with different levels of duplicates. For example, with 25% of duplicates, SmartDedup can achieve 17% of write speedup. This graph shows the read performance. You can see SmartDedup also achieves the best with different levels of duplicates, thanks to our design of page cache index. Then let's look at SmartDedup's resource usage using FIO experiments. We mix different reads and writes to mimic the composition of real-world workloads. The workloads characteristics are shown in the table here. This graph shows the CPU usage. The y-axis is the CPU load, and the x-axis shows the Mix 1 and Mix 2 workloads. SmartDedup on EXT4 is shown in the purple bar, and SmartDedup on F2FS is shown in the orange bar. In this graph, the lower the better. You can see SmartDedup has very small CPU overhead. For example, only 3.3% compared to EXT4 in Mix 1 workloads. This graph shows the battery usage. SmartDedup also performs perfectly, and it actually saves battery by 49% compared to F2FS. And all these experiments are conducted using only 3.5 megabytes of memory. Besides the FIO experiment, we also used real-world workloads to understand how SmartDedup works. We replay segments of traces on Nexus using EXT4. This table shows the trace segments information. This graph shows SmartDedup's performance compared to EXT4. The y-axis shows the percentage of deduplication ratio, write speedup, storage saving, and write reduction of SmartDedup compared to EXT4. And the x-axis shows different trace segments. In this graph, the higher the better, and SmartDedup achieves up to 51% of write speedup and 70% of write reduction. Finally, let's see how adaptive deduplication performs. We evaluated adaptive deduplication on Nexus using EXT4 by replaying trace segment. We show the result of adaptive deduplication based on the workload's characteristics here. This graph shows the results. The y-axis is the power consumption, and the x-axis is the time changes during the trace replay. SmartDedup is shown in the blue line, and SmartDedup with adaptive deduplication is shown in the brown line, and EXT4 is shown in the red line. In this graph, the lower the better, and SmartDedup with adaptive deduplication saves 14% of power overhead with only 8% of loss in deduplication ratio compared to the original SmartDedup. To conclude, deduplication is of importance to smart devices, and it can actually improve performance, resource utilization, and flash endurance. And SmartDedup presents a novel architectural design considering only limited resources. And finally, the traces are already publicly available at Visa Labs' website. You can check it out now. And I want to acknowledge those who have helped with SmartDedup. Thanks to my colleagues and others who have helped with traces and images collection. And finally, welcome to our poster session tonight at 6:30 p.m. and communicate with me. Thanks for listening. I am ready to take questions.
All right, so remember to state your name and affiliation.
Hi, Gala Yadgar from the Technion. This is great work, and I'm wondering if you had a chance to think about whether it could help also on non-smartphone platforms, because you seem to have outperformed other schemes that were designed for in-device deduplication or system-level deduplication. So what's special about smartphones, and would it work for other systems as well?
Thanks for your question. So as you can see, with only very constrained resources, we can already perform this well. So I believe that with other systems, if they have more resources, we can even perform better. But we have not tried on them.
Okay, I think you should. That looks promising. Thank you.
Thank you.
Any other questions? So I have a question. One of the things that you did to enable the deduplication in these standard file systems is go from a one-to-one LBA to PBA mapping to a many-to-one. How does that interact with some of the file systems allocation heuristics or say garbage collection in F2FS? Do they still perform those heuristics at the LBA level?
For the garbage collection, I think they still perform the same.
Peter Matsko from NetApp. One more question. Can you go like few slides back to your evaluation to the trace replay? One more? Yeah, this one. So could you please, the one thing I didn't get is could you please explain why the storage savings is a lot less compared to like the deduplication ratio?
Oh, that's because in these traces, the writes are dominated by the updates to the existing data, so it does not show obvious improvement in storage savings.
Okay, thank you.
You're welcome.
Any other questions? Okay, I have one more. So when you're trying to balance the competing needs on the smart devices, the endurance, the energy usage, you do some throttling. And one of the things you do is you tune the selectivity of when you deduplicate inline. How does that interact with some of the other optimizations you do, like the IDDup scheme of only deduplicating if you have some number of consecutive blocks? Does that help or hurt with locality, or does that have any other interplays with your other heuristics?
Yeah, I think adaptive deduplication, if they involve the IDDup mechanism, it might hurt the locality in the workloads. I think it's just a trade-off in either you choose fragmentation or you either work towards the resource constraint. Yeah.
All right, let's thank our speaker one more time.